We are ready for the next speaker. So it is a huge pleasure to come on stage, Valeria Zuccoli. She holds a Master of Science in Statistics, and she's now an AI scientist with Bettini, designing and developing a computer vision model to work on the edge. Valeria is bringing today a talk about why generative AI models cannot feed themselves. So a huge round of applause for Valeria.
Thank you. Thank you very much, Emanuele. Thank you, everybody, for being here. As Emanuele said, today I'd like to speak to you about an issue that raised with the rising adoption of generative AI systems. So what we are going to see is that probably our generative AI outputs may have a problematic impact on future trained models. But to understand why this is an issue that may be relevant for our future of AI, I'd like to start looking at how much we are using AI today in our daily life. Of course, many people of you know about this chart, that is the number of times papers come with delve, the word delve, in the title or in the abstract. Delve, as surely you know, is one of the most returned words from ChatGPT outputs. So as you can see, this kind of adoption is skyrocketing in the last 2 or 3 years, and that's our destiny since AI adoption is coming more and more inside our life. In another certain point of view, we can also look at Google, that is also a Gen AI company, that says that more than a quarter of their new code is AI generated. AI generated means that some AI generative model generates the code, and engineers and developers just revise it and merely accept it. But now that we understood why this is an important issue for our companies, for our normal life, I'd like to start with you with an example. I'd like to start thinking about training a model that wants to be a generative model for images. I'd like to framework you in the idea that you want to train something to generate images of birds. So what you do is take in your data set, feed that to the model, and ask the model to replicate those kind of data sets. And you ask for the model, then you obtain new generated images, and then decide, okay, I can use these images to improve my own model. And what you end up having is a fish. Well, almost a fish. Because this is something that, of course, does not happen suddenly, but it happens gradually, iteration by iteration. So you start feeding the model your data, then you start adding your iteration-generated data, and then your model kind of forgets the data he started from and ends up with this kind of behavior. What happened in the pipeline is something like that. So you have the real data where you start from, then you fit your model on that, and then you sample from your generative AI model to have a generated data sample. So now you have the first iteration of generated data, and on top of that data, you fit the second iteration of your model. And you go on and on this way, replacing the data of the previous generation with the current one, ending up with some fishes. But what we can understand from this pipeline is that iteration by iteration, our model starts losing important details, such as the feathers of the bird, and starts hallucinating new ones, such as the fins of the fish. So iteration by iteration, detail lost by detail lost, you end up with something you were not interested in, but you were interested in something else that is quite different from what you obtain now. Well, now, how can we start understanding this issue? Our journey starts from this paper of 2023 from UC Berkeley and Stanford, where many researchers start understanding what's happening under the hood. So they started learning this issue inside the image generation problem, even because it's probably one of the most evident area in which you can really tackle this problem on your eyes. So, for example, they trained this stable diffusion model, and they asked this stable diffusion model to generate an elderly woman writing a journal in a charming village square. They decided to go with 5 training iterations with only 100% of real images. Using just real images, what you learn is that you have an output that is quite similar to what you ask for, but you are just using 100% real images per iteration. What if you just use the 25% of these images as generated ones? It's not very a good image, but that's the result. So using just the 25% of the images that are generated from the previous iteration, you see that the same woman, it is full of artifacts, the colors are sparkling, and they are not realistic as you may ask for. But this is an issue that here comes with the 20% of generated data. Is it probably too much? So the researchers started understanding the importance of the percentage of generated data, so they decided to lower very much this percentage. And they started using the 3.3% of the generated data. This is just after 4, not 5, retraining iteration with the 100% of real images and with just the 3.3% of generated images. This time we are not asking anymore for an elderly woman, we are asking for an Hispanic man, but now you see that the artifacts are still real big present in the generated setting. So we are seeing that it's enough to have a low percentage of generated data in our iteration to end up with the collapse of the model. But researchers were interested not only in generated images, but also on text, of course. So they started learning the same model collapse in other frameworks, such as language. They started prompting an open pre-trained transform of 125 million parameters. I know it's not very large, but is for sake of research. Prompting it for something about architecture. So they were asking to complete a prompt about architecture. And while they are learning that with 100% real text, this answers in a good manner, even if we also have some hallucinations, such as the @ symbols that you can see on the answers, while you are using 100% of generated data, what you have is that your architecture prompt starts being full of tail jackrabbits of many colors, black, white, blue, many kind of different jackrabbits inside your prompt that was thought to be an architecture answer. So now that we already understand something about what is the issue on our fingers, it's better to dive inside the definition of this issue and maybe to have some mathematical ideas of what happens behind this stuff. So we can say that model collapse is a degenerative process affecting generation of learned generative models where generated data end up polluting the training set of the next generation of models. Of course, since the next generation of model has this polluted training set, they start misperceiving reality and start outputting what you just saw in the previous slide. But what happens in the pipeline now? So we start from a finite sample of data, since of course you may have big samples for your training sets, but at a certain time you have to end up with your training set and have a finite measure of your training set. You have to finite sample your data, and in this way you see that probable events surely are overestimated, while improbable ones are underestimated. And after this sampling, you have a fitting of the model on the sample you have, as since the model is not exactly wearing the distribution of your data, you surely have an approximation over this time. So what happened is that probable events poison reality, and you have also some tails that are disappearing iteration by iteration. So let's start diving a bit inside finite sampling and seeing how this has some problematic issues. So let's say you have this easy univariate Gaussian distribution. It's a toy example for understand how we can sample from this distribution. And let's say that sampling by sampling, what you can obtain, it's something like that. So you start sampling and then you use finite set of data. So iteration by iteration, your tails are shrinking, your tails are disappearing, and then you have this spike in the middle. So you have a great oversampling towards the mode of the distribution, and you have a great undersampling at the end of the time in the tails of the distribution. Well, what we can see here is the result of this collapse towards the mode of the distribution. So in a variational autoencoder setting, researchers decide to train it just with 100% of real images, and to ask to gives us back some handwritten digits coming from the MNIST dataset that, of course, many of you know. And you see that with 100% real images, the output is quite recognizable. While after 20 iterations with just 100% of generated images, you see that the digits are more or less all the same. What happens here? Here happens that every digit generated, it goes toward the mode digit that we may expect. It is a kind of blend of all the digits we had in the first dataset, since we lost every part of the tails, and since we are just collecting samples from the center of the distribution. But we also had another issue apart from finite sampling. We also have the approximate fitting. That is something that you're dealing with every time you are fitting a model in your life, since approximate fitting affects linear models, boosting models, LLMs, whatever has to approximate the distribution. Since, of course, everybody of you knows about overfitting, so in reality, approximation is also something that we'd like to have in our models. So let's continue our toy example, but this time we are using a Gaussian mixture. So let's think that we have to approximate this distribution with a generated one. And we may end up having a distribution that cannot hold the different modes of our original one. So we end up with a distribution that is quite different from the other, but is simpler to model. So our model is more keen on having this kind of approximation. What happened here is that you see the creation of artifacts. Since in this area, you can see that the original distribution did not have any kind of sample, but at the same time, it is at the center, at the mean of the original distribution, this starts to be our generated distribution. In the image point of view, coming back to stable diffusion and coming back to our lovely older Hispanic man, you can see that in the 50% of generated images and 50% of real images, or with 100% of generated images, you are converging to a mode image with some artifacts inside. So you see the bubbles on the skin, you see the completely losing of the backgrounds, and you see that iteration by iteration, starting from the third, but also from the fourth iteration, you are going towards an image that is more or less ever the same. So we are converging to a kind of mode image that is having all the artifacts and the problem of finite sampling that we started from. But when I encountered this issue and I started reading these papers, I was looking for some mathematical proofs, since, okay, the ideas are nice, the charts are nice, but I'd like to see the mathematics. So I'd like to start from the discrete case, since researchers started from discrete case to understand what's happening under the hood. I'd like so to start with Xi, that is a discrete distribution with just a random distribution in the discrete case. Here it is a chart with just 6 categories, but you can imagine whichever discrete distribution you have in mind. So, iteration by iteration, what researcher proved is that this is a nice Markov chain in the discrete case. Why it is a Markov chain? Because a Markov chain, it's a stochastic process in which the state that you have now just depends on the state you have on the previous iteration. So if you keep in mind what we are going to do, that is training a model on the current generation of generated data, this is exactly a discrete Markov chain. But iteration by iteration, Markov chain leads you somewhere that is, in reality, in this case, an absorbing state. What is an absorbing state? Well, you can see that a Markov chain with absorbing state is a chain in which you have some categories from which you cannot go out. So when you enter this category, when your variable starts being, in this case, 0 or 3, you cannot be anything else in the future, because no arrows in the graphs gives you back to the other states. But in a Markov chain with absorbing state, you end up having every realization of your variable coming inside those states and never giving outside. So what they demonstrate is that Xi is a Markov chain that collapses in a delta Dirac as I goes to infinite. And the delta Dirac is the distribution that goes with every probability, in this case, on the absorbing state of your Markov chain. This was the easy discrete case. But we have also a demonstration, a proof in the continuous case. So the same team of researchers started learning about the normal distribution in this setting. So they started using a normal distribution with standard parameters. They estimate those parameters via their finite sampling and via their data set with the unbiased estimators. Once they have the unbiased estimators, they put them back inside the normal distribution and go on and on in this kind of circles. What happened is that the expected value of the Wasserstein distance between the original distribution and the current generated one diverges and goes to infinite. So what happened is that the distance between the original distribution and the current one is getting greater and greater, so these distributions are not the same anymore. So we are trying to estimate something that is no more what we have in our real case. Moreover, the variance goes converging to 0. So if the variance goes towards 0, what happened is that also in this time we have a convergent state on a delta Dirac. So we have a model that both in the discrete case and in the continuous one converges to a single delta Dirac function that is clearly different from what we started from. But now that we understood what we are having, now that we understood the issue, some researchers decide to try to understand if is there something that we can do to remediate this issue, since it is really something is close to our daily life. So they started with the older Hispanic men with this kind of setting, so 75% of real images and 25% of generated, and they say, okay, let's do this. Let's take just 100% of real images. And iteration by iteration, I'd like to see if I can heal the problem that I already have. And the result is that probably not. So, of course, you see that in particular in the background, you have that the artifact number is getting lower, but anyway, the bubbles on the skin are still present on the main face. Of course, Stable Diffusion can be just a small model in comparison with other models. But anyway, this is something that really affects a model that is always trained now in the retrained phase with just real images. So what we can do now is, okay, retraining is not possible anymore, so our only opportunity is to watermark our generated content in a human-readable format, in a machine learning-readable format, so that the future generation of AI cannot use these outputs because they recognize them. And we also have the opportunity to use some models, such as Video Seal or SynthID, that may help us designing this kind of difference. But of course, this is also depending on our will, since it is not embedding in every Gen AI model to have this kind of watermarking technique. So still, I ask myself, is this our future? So internet gives us big data, and Gen AI gives back other big data to the internet. But in reality, what happened is that we still have some kind of hope. As for now, we just learn about what happened in model collapse in the replacing framework. So we starting with the original data, we fit a model on it, then we decide to generate some data and fit the model just on the generated data, and so on. But what if we use a probably more realistic idea, such as the accumulation idea? So in our training sets, we are not using just the last trained samples. We can use also the previous samples coming from the previous generation, and we can also include the original data in every part of the setting. Well, this is an interesting point of view, since it has been proved that for linear and logistic models, we have an unbounded test error that goes up linearly with the numbers of the iteration in the error test in the replacing setting, while we have an upper bounded test error on the accumulation setting. And the upper bound is p²/6, and p²/6 is less than 2. So starting from the second iteration, we starting have some enjoyable opportunity to have this test error that is easier to understand and not diverging. And this is really important for our future application. But this is just for linear and logistic model. What about variational autoencoder and image generation? Well, it has been proved that more or less it has the same answer. So you can see that in the replacing setting, you have a linear increase in this test error, while on the other side, you have that more or less the 8th iteration is at the same error test as the first one. So it's something that is a hope for us to understand this kind of directions. And we also have something about other diffusion models for molecular generation in which you have a big spike at first in the model fitting iterations in the replacing setting, while you have a quite easy slope on the other side in the accumulation setting. This spike is also due to the approximate fitting in particular that we started learning at first, since probably in this setting, the model has hard times following the original distribution from the starting point. Then this error is not healed anymore in iteration over iteration. But we have also another important result I'd like to share with you that is even better than what we saw since now. So Google researchers and US California University decided to understand what's inside this training process for LLMs. LLMs share an important property that is the strength of weak data for their training. What does it mean? Let's start from the complete framework of the research. So they start taking a prompt from your training set, then you feed it inside the LLM, and then you obtain a number, let's say K, of responses. Why they are using this kind of many responses? Well, you surely know that depending on the temperature of the setting and other parameters, you may have different responses from the same prompt. Then you have to evaluate the quality of this kind of samples, of this kind of responses. And in this particular research, quality is intended to be as binary. In the future work, they are committed to work also on continuous quality between 0 and 1. So after this quality evaluation, what you do is to choose the best response in K response. This means that if you have at least one response that has quality 1, this will be the answer, the response you are going to take. If no response reaches the quality of 1 but still is to 0, then you are going to pass the 0 response. These best responses are all collected in a best response set. So here you have a percentage of these responses that is high quality and a percentage of that has low quality, because the LLMs could not give this kind of high quality answer. Now you have both quality and low quality response in the same set, but you can, of course, divide them since it is just a binary distinction. So you have low-quality prompts on the side and high-quality prompts and their responses on the other side. Now, the high-quality prompts and responses are good enough for us, so we don't have to process them for much. But we are better understanding what's inside the low-quality prompts and how to manage them for our future training set. So our setting decided to use a beta weak labeler. This beta weak labeler needs to have at least beta prompts correctly labeled inside the processing. So beta is not needed to be big, but is important to be a fraction of the prompts that has been at least completely correctly labeled. What does it mean? This means that you don't have to correctly provide an answer to all the prompts you have, but it's enough to have a small percentage of these prompts to have a good answer. Once you have this beta weak labeler labeling these low quality prompts, and this labeler may be a human, so we have the opportunity to have also a human in the loop in this framework, we have the weakly labeled prompts, and we also remember that we have also a set of high quality prompts and responses. Now, what we can do is to mix the weakly labeled prompts with the high-quality prompts and responses in a weighted mixture and having our training set. Now, our training set that is mixing this kind of different prompts can be used for training another LLM. So the next iteration of the same LLM we were starting from starts from learning from here, from this training set that we are just using. And now what you can do is to keep on going. So keep giving the LLM the prompts, giving the responses, selecting them, and going towards this way. Now, what researchers proved in their paper is very important, since they demonstrate that this procedure, this iterative procedure, does not go only to a good LLM, but it converges to an optimal LLM. So the LLM is not stable at the same performance as it started, but it's getting better and better and better. Of course, if beta is high, it is faster to reach this kind of convergence. But this is not needed. We just need more iterations to go. So since we have also the idea that we can use synthetic data, but we also need data curation, we can now say that we can start from birds and end up with other birds of the same kind. It just needed to us to have a look inside the data, to open the data set and to curate your data in order to get your model getting better and better iteration by iteration. Now I leave you some of the resources of the paper. And I am Valeria. I am a data scientist in Bettini. As probably you understood, I am a statistician by education. And I'm learning every day about computer vision and Gen AI. And I hope you enjoyed the talk.
All right, unfortunately, we're running a little bit late, so we only have time for one question. Who wants to be the lucky guy?
Oops.
Yeah, great.
Hi, thank you for the talk. Do you think that this data curation that you explained in the last slide is actually happening at web scale, meaning that people are doing this filtering implicitly, or do you think that companies should invest a lot to filter this data nevertheless?
Well, I think that companies should invest, of course. In particular, the companies that are training actually LLMs and generative AI models, since you know, the web is full of content that I can generate, everybody can generate, and I may be not so attent in my spreading of AI-generated content. So I believe that more data curation should have been performed on the training side of the pipeline. Since even you also have to think that people that publish stuff on internet maybe do not know what really data curation is sometimes. So it's hard to understand. Also because you have to do data curation in particular when you have the whole picture of your data set. And you are just publishing a post on LinkedIn or an image on the website, so you actually even don't care of this kind of issue.
All right, thank you again, Valeria. Another round of applause, please.